The universe is not atoms, it's just data. The photon in the lab shouldn't care who's watching. Yet the instant we look, its reality changes. Path chosen, probability collapsed. Now stretch that to a black hole. Information plunges in, Hawking radiation drifts out, and the math says the story inside should be gone forever. But physics insists information can't disappear. So where did reality hide it? To understand why a universe built from atoms started behaving like data, we need to rewind. Black holes, holograms, quantum codes, none of this was meant to describe us. And yet, one idea keeps returning. The cosmos isn't stuff obeying laws. It's information obeying logic. Matter starts cracking, from atoms to bits. It starts with a question that should have been boring. How much stuff can a black hole store? In the early 1970s, Jacob Bekenstein pressed on that puzzle and found something nobody expected. The storage capacity. The entropy didn't scale with volume like a bookshelf getting bigger. It scaled with surface area. More skin, not more space, meant more information. The interior stopped mattering. The boundary kept the books. Stephen Hawking's calculation made it worse. Black holes emit thermal radiation, now called Hawking radiation, as if they're hot. Thermal means random. Random means no information. If a black hole evaporates to nothing but heat, the details of what fell in, stars, planets, would be erased. That breaks quantum mechanics. Information can be scrambled but not destroyed. Bekenstein's area law was a clue. If the information is on the surface, the event horizon, then maybe Hawking radiation isn't empty. Maybe it's a careful leak, a cosmic checksum oozing away, carrying out the boundaries record bit by bit. The interior turns into an account you never access directly. The surface is the ledger. That's not a metaphor, it's the math. But the truly uncomfortable step came next. Gerard T. Hooft and Leonard Susskind asked, if a black hole's interior can be fully encoded on its boundary, why not any region of space? That's the holographic principle. The 3D world might be the output. The 2D boundary might be the code. It sounded like philosophy until Juan Maldacena gave it teeth. In 1997, he showed a duality, add SCFT, where a specific negatively curved, gravity-filled universe is exactly equivalent to a quantum field theory living on its lower dimensional boundary. The boundary knows everything for that setup. Space and gravity emerge from the way information is entangled there. You don't need the interior to compute the interior in those models. Physicists then discovered something even more practical hiding in the abstractions: error correction. Holographic models behave like quantum error-correcting codes. Lose some boundary data, and the bulk space, the apparent inside, can still be reconstructed. Stability emerges because information is redundantly encoded. Reality's robustness looks less like solid matter and more like a well-designed code that won't crash when you flip a few bits. Meanwhile, other threads converged. John Wheeler's phrase, "it from bit," stopped sounding whimsical. If the maximum information in a region is bounded by its surface area, the universe behaves like a finite capacity system. If space and time themselves carry information limits, then what we call physics looks like rules for transforming bits, not pushing atoms. Listen to the quantum scale. An electron isn't a tiny ball, it's a spread of possibilities until measurement. Entanglement ties distant particles so tightly their shared information ignores distance. That spooky correlation isn't a wire across space, it's adjacency in the underlying information structure. Measurements are not just readings, they're updates to the state of a computation. The skeptics pushed back. Computation suggests steps and grids. Einstein's symmetries don't like stuttered time or jagged space, but there's a way around naive discreteness. Replace rigid lattices with relationships. In causal set and hypergraph approaches, you don't place dots on a ruler. You record which events can influence which. The network's pattern matters, not the imaginary spacing of its lines. Distances and geometry emerge from the information flow itself. This is how relational approaches aim to sidestep the symmetry trap, letting Lorentz symmetry emerge rather than hard breaking it. If this all feels remote, hold on to a human moment. The CEO eating breakfast when the call comes about a merger. Coffee cup slips, shatters, because a decision made months earlier finally reaches his kitchen. That's how information propagates. In physics, the decisions are rules. The shattering is a measurement. And the kitchen is the emergent world we live in, solid until a boundary update says otherwise. Now remember black holes. If their surfaces store the inside, they're not just monsters, they're processors. Seth Lloyd went further. Count the logical operations the universe could have performed since the Big Bang. The number is staggering, but the point isn't the exact count, it's that you can count it. The universe can be described in the same language we use for algorithms, not metaphorically, formally. This shift reframes familiar constants. The speed of light isn't only about moving stuff fast, it's an upper bound on information transfer. Planck's constant looks like the minimum action per update. The Bekenstein Bound is a memory limit. Each law reads like a hardware constraint in a system that prioritizes consistency, compression, and recoverability over tactile thingness. So atoms didn't vanish. They became user interface. We still sit in chairs and boil water, but beneath the icons are protocols. Entanglement patterns sewing geometry, error-correcting redundancy, preserving stability, and boundary encodings that make 3D feel local and continuous. When we test gravity waves or smash particles, we aren't peeling reality open. We're poking the operating system and watching how it handles load. One detail will matter later. In the most successful holographic models, space gets stitched by entanglement. Tear the stitches, reduce entanglement, and regions drift apart. Increase it and distances shrink. Geometry is policy. Gravity becomes the way information chooses to organize itself. The crack in matter wasn't a collapse, it was a reveal. We thought we lived in a warehouse. We're in a data center. Quantum rules that behave like code. Start with the most famous riddle in the lab, the double-slit experiment. Fire single photons one at a time toward two narrow openings. If you don't look, a wave-like interference pattern builds up on the screen, bright, dark, bright like ripples crossing. But place detectors to ask, which slit did it take? And the pattern vanishes. The photon behaves like a particle. The only difference is a yes or no query. That's not a billiard ball changing its mind. That's a system responding to a question and input by updating its state. Code runs, output changes. Entanglement turns it up. Prepare a pair of particles whose properties are linked. Pull them miles apart. Measure one and you can predict the other instantly. No signal flew faster than light. Instead, the information describing their joint state was already shared. In a holographic world, far apart in 3D can still be neighbors in the boundary's data structure. The distance that matters is informational. Entangled bits sit next to each other in the code, even when their projections look separated. This is where the universe starts to feel like a quantum computer. A classical bit is 0 or 1. A quantum bit, a qubit, can be a superposition of both until a measurement. Combine qubits and the space of possibilities explodes. Entangle them and you create structure across that space. Quantum algorithms, like those being built in labs right now, don't just try choices in sequence. They choreograph interference so wrong answers cancel and right ones add. The trick isn't speed, it's parallel possibility sculpted by rules. Now bring that lens back to physics. Quantum theory says systems evolve smoothly and reversibly according to the Schrödinger equation, until a measurement when outcomes appear with specific probabilities. Two modes of update: deterministic and unitary between observations, stochastic and decisive when you couple to a measuring apparatus. From a code perspective, these are two layers of logic: continuous evolution, then a read-write event that fixes values in a particular basis. We don't yet know the full story of how consciousness fits here, and we won't pretend. But the pattern is clear. The universe keeps options open, then commits when queried by an interaction that can amplify a microstate into a macroscopic record. The commitment matters. Every record, every irreversible trace costs energy. Landor's principle tells us erasing a bit requires a minimum energy toll. Information is physical because changing it disturbs the world. That's why measurements heat apparatus, why computation needs cooling, why there's no free lunch when you compress, copy, or delete. Thermodynamics and information theory aren't separate books, they share margins and page numbers. Black holes bring this together. Their entropy scales with surface area. Bekenstein's law and Hawking radiation return scrambled information. In AD-SCFT, the boundary quantum field theory evolves unitarily. No information is lost. The bulk gravity story is a dual description that emerges from boundary entanglement. The Ryu-Takayanagi formula even equates the entanglement entropy of a region on the boundary to the area of a minimal surface in the bulk. Translation: geometry is bookkeeping for who's entangled with whom. And error correction sits at the heart of it. In holographic toy models and related tensor network constructions, the mapping from boundary qubits to bulk degrees of freedom acts like a code. Lose part of the boundary, noise, deletion, and you can still reconstruct the interior operators from what remains. That's why the bulk feels stable in these models. It's not mystical robustness, it's redundancy engineered by the way the encoding works. Skeptics point to continuity. If everything is information, where's the grid? We address that trap. Replace coordinates with relations. Who can influence whom? Causal sets and hypergraph programs catalog causal adjacency, not meter-stick distance. Lorentz symmetry can, in principle, emerge in that world because nothing privileges a universal clock tick. Time steps become update events constrained by causality, not metronome beats. Sabine Hassenfelder pointed out the pitfalls of naive lattices. The response wasn't to abandon computation, it was to deepen it, making the substrate relational so symmetries can emerge. Meanwhile, the constants look like compiler flags. The speed of light caps how fast influence can propagate. Planck's constant sets the granularity of action. The Bekenstein Bound limits storage per area. These aren't decorations. They're constraints that any valid program of physics must satisfy. Inside those constraints, complexity blooms because the rules allow feedback, copying with mutation, and networks that rewire themselves. You already live this. Close your eyes. Memory is an encoding that resists noise. Perception is inference from finite, lossy data. Your brain exploits redundancy across neurons, across time, to reconstruct a stable world from partial signals. It's quantum mechanics at the bottom and error correction all the way up. Consciousness is its own conversation, but we can say this. Minds evolve to navigate an information-limited environment by becoming efficient compressors and predictors. Now flip the viewpoint. What if we're not just passengers inside the computation but components? Every observation you make is a tiny measurement event, a local collapse that writes a bit into the shared record. In that sense, we participate in selecting realized branches from quantum possibility, not as magicians, as collaborators constrained by the same rules that govern stars and black holes. Seth Lloyd once estimated the universe's total logical operation since the Big Bang. The number is vast, but that's not the headline. The headline is that you can think of cosmic history as computation without breaking any laws. Each particle interaction, each entangling scatter, each decoherence event is a line executed in a program that compiles into galaxies, chemistry, and cells. Here's the payoff. When quantum rules behave like code, gravity stops being a mysterious curvature imposed from above. It becomes the large-scale pattern that emerges when information arranges itself to be consistent, compressed, and recoverable. Stitch entanglement tightly, and space knits closer. Thin it, and space loosens. The force that keeps your feet on the ground may be the universe's way of keeping its story straight. The hologram, reality as a storage hack. Start with the constraint that changed the map. The Bekenstein Bound says the maximum information in any region isn't set by volume, it's set by the area of its boundary. That's not a poetic idea. It's a hard limit that shows up wherever gravity gets serious. If you try to pack more bits into a region than its surface can encode, gravity answers by making a black hole. In other words, nature enforces compression. The universe saves to the surface. That's the storage hack at the heart of the holographic principle. If all the physical detail inside can be represented on the outside, then the cheapest way to store reality is to write it to the boundary. Not because the universe likes metaphors, but because that's the only way to keep information consistent without violating gravity's bookkeeping. The interior becomes a reconstruction, a view created on demand from encoded data. ADS-CFT made this operational. In Maldaisner's duality, every bulk process, falling, colliding, curving, is mirrored by boundary dynamics. You can solve a gravity problem by doing quantum field theory on the edge, and it isn't approximate. In the right setups, it's exact. That's why it's a hack and not a hand wave. Two descriptions, one physics and the boundary one has no gravity at all. Gravity emerges from entanglement and correlation patterns, not from a fundamental force law etched in stone. Here is where the Ryu Takuyanagi insight changes the picture. In AD-SCFT, the entanglement entropy of a boundary region equals the area of a minimal surface in the bulk that hangs from that region's rim. Entropy on the edge draws an invisible soap film inside, and its area gives you the number. You can flip that around. If you know how parts of the boundary are entangled, you can infer the shape of space in the bulk, within the scope of those models. Geometry becomes a ledger of who is correlated with whom. Now add error correction, and the hack becomes robust. In holographic codes, the mapping from boundary qubits to bulk operators is redundant by design. You can lose pieces of the boundary and still recover the interior operator from the remainder. That's why the inside can survive noise. It's not that the bulk is invulnerable, it's that the map recovers it from multiple overlapping encodings. A crash-resistant file system masquerading as a universe. If space is stitched by entanglement, gravity is the tendency of that stitching to tighten where information concentrates. Put mass energy in a region, and you change the pattern of correlations on the boundary. The minimal surfaces that dip through the bulk reshape, and the geometry they define curves. That curvature is what we call gravity. It's not a bolt-on. It's an accounting response to how information is distributed. Skeptics ask, our cosmos is anti-de Sitter space. True. The most precise duality lives in negatively curved universes with neat boundaries, but the ideas have legs. Physicists have generalized pieces of the story to spacetimes closer to ours, and the methods, tensor networks, entanglement wedges, quantum extremal surfaces, keep finding new uses. Even when a precise duality isn't established, a recurring pattern appears. Area tracks entropy, and geometry tracks correlation. This is more than math pride. It changes how you think about locality. In the bulk, points sit next to each other because the boundary encodes them with heavy shared entanglement. Reduce those ties and the bulk points drift apart. In extreme cases, tearing entanglement, you can disconnect regions that still look adjacent in naive coordinates. Locality is a property of the code structure, not an axiom. You already use versions of this in technology. A photograph stored with redundancy can be reconstructed after partial loss. A video stream stays smooth because error-correcting packets fill gaps. Holography is that idea pushed to the limit. The file of a whole region of space is stored on its boundary with enough redundancy to rebuild the inside under noise and loss. When we say the world is a projection, we don't mean it's fake. We mean projection is an efficient way to keep the world consistent when memory lives at the edge. There's a deeper economy playing out. The laws we measure look like rules optimized for compression and recoverability under the Bekenstein Bound. The speed of light caps update speed across the code. Planck's constant sets the grain of action per change. The area law forces surface-based storage. Within those constraints, the holographic architecture minimizes cost. Compute on the boundary, reconstruct the interior only as needed, keep redundancy high so local errors don't cascade. Black holes, once villains, become model devices. They saturate the bound. They scramble information fast, then return it late, highly mixed, but recoverable in principle if quantum gravity is unitary, as AD-SCFT strongly suggests. They show what happens when you push storage to the limit. The screen goes black, the file is still there, and the universe insists you can't read it faster than the rules allow. So the hologram isn't a trick, it's a policy. Reality favors surfaces because surfaces can carry the load without breaking quantum mechanics or gravity. Space is the visualization that helps finite creatures like us navigate the output. And gravity is the visible side effect of the code keeping its ledger balanced at the edge. We thought solidity made the world real. Maybe what makes it real is that it's stored well. Error correction in the fabric. If geometry really tracks entanglement, then stability has to come from something smarter than luck. Codes don't just store, they protect. That's the quiet revelation inside holography. The bulk feels reliable because the boundary acts like a quantum error-correcting code designed to keep meaning intact while noise does its worst. Think of a simple story. You write a sentence on 3 separate cards and hand them to 3 friends. One card gets smudged, but 2 are clean, so the message survives. That's classical redundancy. Quantum codes go further. They spread a qubit state across many physical qubits so that no single piece reveals the whole, yet enough pieces can reconstruct it. Lose a chunk, and the logic still recovers the original. Holographic duality builds that logic into the world. The mapping from boundary degrees of freedom to bulk operators is deliberately redundant. A bulk excitation, what you'd call a particle or a local disturbance, can be reconstructed from multiple, overlapping regions on the boundary. Not one unique place, but many different entanglement wedges that each contain enough of the code to rebuild the interior operator. That's why the inside isn't fragile. It's supported by a web of overlapping encodings. Now add the Ryu Takuyanagi picture back in. Those minimal surfaces hanging into the bulk carve out the entanglement wedge for a boundary region. If your wedge contains a bulk operator, you can, in principle, reconstruct it from that region's data alone. 2 different boundary regions with different wedges can each recover the same bulk operator. That's error correction in action, multiple recoveries from independent views. This isn't armchair poetry. Toy models using tensor networks, MERA-like constructions, and HOPPY codes make the redundancy visible. You lay down a tiling that maps a few bulk degrees of freedom into many boundary legs through layers of isometries. Cut off some legs, simulate loss, noise, or measurement, and the network still decodes the bulk state from what remains. The picture looks like a geometric snowflake, but the function is pure reliability. Local damage at the edge does not instantly tear a hole in the middle. Here's the human moment. A mission control team loses a telemetry channel during re-entry. Not a problem. Crosschecks reconstruct the missing numbers from other feeds. Meanwhile, across town, an engineer's laptop crashes, but autosave rebuilds the document from fragments. Neither feels magical because we intuit how redundancy works. Physics appears stable for the same reason. Only the redundancy is woven into the entanglement that shapes space itself. Error correction also clarifies an old worry. If the inside of a black hole is encoded on the horizon, and Hawking radiation carries information away, how does the story stay consistent? In a code, information can be delocalized without being duplicated. Early radiation is nearly useless. As evaporation proceeds, subtle correlations accumulate until, past the page time, recovery becomes possible in principle. No cloning happens. The code just reassigns where the recoverable support lives, first the horizon, then increasingly the radiation. What looked like paradox is a bookkeeping mistake ignored by anyone who builds reliable systems for a living. There's another payoff. Codes explain why low-energy bulk physics looks local even though the true encoding is wildly non-local on the boundary. Locality in the interior comes from how logical operators are supported on many boundary regions in a way that preserves their commutation structure. You act on one logical degree of freedom, and others barely notice, even though the physical qubits overlap. That's how you get particles that don't instantaneously talk across the room despite being encoded by shared boundary stuff. The flip side is fragility with purpose. Not every error is harmless. Corrupt the wrong pattern, enough adjacent boundary regions, and reconstruction fails for the corresponding interior wedge. In spacetime language, that looks like a horizon forming or a region becoming inaccessible. The code announces without drama, you asked for more than the redundancy can bear. Geometry reflects the same message. Now connect this back to emergent gravity. If entanglement patterns tighten where information is dense, the code must continually rebalance to keep logical operators recoverable under the Bekenstein Bound. That rebalancing shows up as curvature, geodesics bending, minimal surfaces reshaping, light cones tilting. Gravity is the system's way of maintaining decodability under finite storage and finite speed update constraints. You can see the same theme in our machines. Quantum computers fight decoherence by encoding logical qubits in surface codes that tolerate local errors. Classical networks maintain consensus via parity checks, read, Solomon blocks, and distributed ledgers. All of it is about preserving global truth when local pieces misbehave. The universe runs the deluxe version, a relational code that makes space from entanglement and keeps meaning alive as noise, heat, and measurement chip away. This perspective also reframes why we don't notice microscopic reversibility. Measurement writes outcomes into macroscopic records that the code now treats as constraints. You can't just unring the bell because the correction logic has accepted the update. Entropy increases not because information disappears, but because it diffuses into degrees of freedom that would require astronomical coordination to reassemble. So when a gravitational wave crosses Earth and LIGO catches a wobble in spacetime, think of it as a code pulse, a temporary reshaping of which boundary partitions best reconstruct which interior modes. When cosmic rays hit the atmosphere, you're watching the system mix, spread, and correct. And when you remember a name after forgetting it for days, redundancy saves you again. The trace was there, encoded in overlaps, waiting for a cue to decode. Error correction isn't a metaphor glued to physics. It's the policy physics seems to follow to exist at all. The world stays legible because the code that makes it prefers recoverable stories over fragile ones, and writes them redundantly on the only medium big enough to hold them: the edge. Energy, computation, and the cost of knowing. Start with a simple claim that's easy to miss. Every time you learn something, the universe heats up. Not poetry, physics. Landauer's principle says erasing one bit of information costs at least kT-ln2 of energy dissipated as heat. At room temperature, it's tiny. At cosmic scales, it's policy. You can't change the record for free. Measuring, writing, or resetting bits pushes entropy somewhere. Knowledge has a thermodynamic bill. That bill shows up everywhere. Open your laptop. Fans spin because logic flips shed heat. In a lab, quantum processors sit in dilution refrigerators because coherent superpositions hate warmth. In biology, ATP pays to maintain low entropy order in neurons so memories can persist against noise. The same rule stitches from hardware to nervous systems to galaxies. Information is physical, so processing it taxes energy and raises entropy. This cost ties directly to limits. The Bekenstein Bound gives a maximum information capacity for a region set by its boundary area. The Margulis-Levitin bound caps how fast a system of given energy can compute. Seth Lloyd combined these into a back-of-the-envelope census. Since the Big Bang, the observable universe could have performed roughly 10^120 operations on about 1090 bits. Don't fixate on the exact exponents. Focus on the concept. There's a finite ledger of memory and a finite clock speed. Even cosmology respects throughput. And the famous c, the speed of light, doubles as a bandwidth limit. No influence travels faster because no record can propagate quicker through the code. Planck's constant h sets the minimum action per update, the grain of quantum change. Together, these constants look less like decorations and more like compiler constraints. They define the rates and resolutions at which the cosmic program can step without breaking consistency. Thermodynamics, then, isn't an afterthought to computation. It's the ground truth. Entropy increases because records proliferate and scatter into degrees of freedom you won't coherently reassemble. Computation consumes free energy to produce ordered outputs. It pays by dumping heat into environments. Even the arrow of time might just be the direction in which the universe can still afford to compute, toward higher entropy states that have more micro-descriptions to encode the macroscopic story. Black holes are the extreme accountants. They saturate the Bekenstein Bound, maximizing storage per area. They're also the fastest information scramblers we know, spreading local data across horizon degrees of freedom in times that scale like the logarithm of the entropy. But they never violate the cost. Hawking quanta dribble out at a temperature inversely proportional to mass. To return information, a big hole must radiate for a very long time, paying the energy price bit by bit while preserving unitarity. Recovery is possible in principle, not cheap in practice. Bring it closer to home. A scientist calibrates a detector for a week before a 1-second measurement. Most of the energy burned wasn't the click. It was preparing a state resilient enough that the click would mean something. That's the hidden economy of knowing. Reliable bits require low temperatures, isolation, redundancy, and time. Resources marshaled to beat back noise long enough to etch a mark into the world. The cleaner the bit, the higher the cost. Now flip the camera toward life. Brains are dissipative computers. Your cortex runs at about 20 watts, juggling spikes that minimize predictive error under metabolic budgets. When you recall a face, you don't pull a perfect block from a library. You reconstruct a best guess from overlapping codes, paying energy to reduce uncertainty just enough to act. Intelligence, seen this way, is an algorithm for spending energy efficiently to compress experience into useful predictions while preserving flexibility. The same trade-off shapes technology. Quantum error correction lets us compute coherently, but each protected logical qubit demands many physical qubits and constant syndrome measurements, overhead paid in energy and complexity. Classical error correction keeps networks reliable, but parity checks and retransmissions cost bandwidth and power. Fault tolerance isn't free. It's purchased by redundancy and maintenance. Cosmology writes the largest bill. As expansion continues and stars exhaust fuel, accessible free energy dwindles. Computation slows. If the dark energy density stays near constant, horizons fix how much of the universe can ever be causally coordinated. That means there's a finite budget of computation per observer. Heat death isn't just cold, it's quiet, a time when gradients flat and the cost to compute anything meaningful exceeds available energy. The lights don't go out, the process idles. Does this make meaning feel small? It shouldn't. It makes it precise. We inhabit an era with gradients to spend, entropy to grow into, and bandwidth to write records. That's why complexity blooms now. Stars forge elements, chemistry explores phase spaces, organisms learn. The universe is in a high-throughput phase where structure can be computed, stored, and corrected against noise at bearable cost. And the holographic architecture dovetails with this economy. Store to surfaces because it's cheaper and safer. Reconstruct interiors on demand to avoid waste. Use entanglement to compress correlation. Root geometry so signals don't exceed bandwidth. Gravity appears as the bookkeeping that keeps decodability under budget. Beauty is the byproduct of a system optimizing consistency under constraints. So the next time a measurement surprises you, remember, you paid for that bit. A tiny jolt of energy left somewhere so a new fact could join the ledger. In a universe that computes, learning is not free, but it's worth the heat. Time without a master clock. We've been treating updates, collapses, and corrections like steps. But whose steps? If the universe is computation, does it tick on a single cosmic clock? Here's the twist. The code runs without a master timer. Time, the thing we swear we feel, may be an index we impose on correlations, not a gear grinding beneath them. Quantum theory hints at this. Between measurements, states evolve smoothly, but between is our story. The formalism lets you slice evolution with any parameter as long as you keep the relationship straight. In gravity, it gets starker. General relativity doesn't prefer one time. It gives you a spacetime where different observers carve different nows, each consistent. There's no central metronome. There are only causal relations. What can influence what? Holography deepens that. The boundary theory has its own notion of time, generated by its Hamiltonian. The bulk inherits a sense of before and after from how entanglement wedges nest and how minimal surfaces shift as boundary states change. But there isn't an extra hidden clock behind the mapping. Bulk time is the way reconstructions order themselves, so cause never loops back to break consistency. In other words, chronology is policy enforced by the code's causal structure, not a universal second hand sweeping the cosmos. Think of a city at night. Traffic lights blink on their own schedules, restaurants close at different hours, people sync to meetings, trains, or sleep. The city functions because each timeline respects a few shared constraints. Don't crash, don't block, let flows resolve. That's how the universe keeps time. Local processes coordinate via light cones and entanglement, not by consulting a celestial clock tower. At the quantum scale, the page, Wooter's perspective, offers a clue. You can build time from correlations between a subsystem you call a clock and the rest. The joint state is static. Conditional states evolve when you read the clock. No external time, just relational change. In a holographic universe, the boundary has plenty of good clocks, complex degrees of freedom with stable periodicities. Bulk dynamical stories emerge when you condition on those. We experience flow because we are embedded clocks correlating with other processes. This view reframes the arrow of time. It isn't painted by a master clock. It's carved by entropy and memory. Records pile up in one direction because writing them is irreversible and costly. Landor's principle doesn't pick a universal tick, but it does bias which sequences of updates become typical, those that spread information into many degrees of freedom. The arrow is the direction in which the code most easily supports redundant, recoverable records under finite resources. It also resolves a common confusion about the present. In relativity, simultaneity isn't absolute. In computation, neither is a global step. Updates happen where interactions allow, constrained by causality. In causal set and hypergraph approaches, you add relations. This event precedes that one, without imposing a rigid layer ordering. Many partial orders can represent the same physical situation. Your now is a slice through that order, chosen by motion and method, not by decree. But if time is relational, what about the universe's beginning? Was there a first tick? From the boundary view, you don't need a start in external time. You need a low complexity, low entropy state that allowed correlations to grow and structure to compute. Call it the boot sequence if you like, a condition from which entanglement spread, geometry inflated, and new records could be written without immediate saturation. Before, that is not a forbidden question. It might just be meaningless because the correlational scaffolding that makes before coherent didn't exist. Here's a human-scale echo. You sit with an old friend and hours fly. Another day, minutes slog. The external clock marches, but your experience time is correlation density, how many meaningful updates your brain integrates per unit metabolism. The system computes. Your felt flow tracks successful prediction and surprise. In the cosmic version, how time passes locally depends on how degrees of freedom can exchange information under constraints like gravity and temperature. This doesn't demote time, it roots it. Proper time along your path remains as sacred as ever, measured by your clock, shaped by gravity, unarguable in its readings. What changes is the fantasy of an external stagehand counting beats for all things at once. The universe keeps itself consistent by respecting orderings that maintain decodability. That's enough to grow histories, define causes, and let memories mean something. And it answers a subtle worry. If the universe computes, who presses run? Nobody. Running is what it means for relations to exist and constraints to interlock. The code is the world. Its progress is the emergence of correlated records within a finite capacity, finite bandwidth architecture. Time is how those records line up when read by subsystems like us. So the next time a clock chimes, hear it as a local agreement, not a cosmic pulse. The computation doesn't wait, it doesn't hurry. It maintains causal order, honors costs, and lets entanglement sow a living chronology from correlations alone. In a universe without a master clock, consistency is king, and that's all time needs to be. Building space from entanglement. We've said geometry is policy and gravity is bookkeeping, but how does space itself get built from information? Start with a simple instruction: connect what's correlated. If two sets of degrees of freedom share lots of entanglement, treat them as neighbors. If they barely share any, push them apart. Do this everywhere, and you don't just label relationships, you lay down a metric. Distance becomes a measure of how much you have to cut through entanglement to separate regions. That's the spirit behind using tensor networks as scaffolding for space. In a MERA-like construction, you stack simple tensors, little boxes with legs in layers that coarse-grain information. Bottom legs feed top legs, local details compress into broader features. If you trace a path between two boundary sites, you count how many tensors you cross. More cuts, more distance. The pattern isn't drawn into space, it defines space. The network's geometry is a map of correlation structure, not decoration on top of it. In holography, this intuition goes technical. The Ryu-Takayanagi formula ties entanglement entropy on the boundary to minimal surfaces in the bulk. Imagine a wire frame on the boundary, your chosen region. A soap film dips into the bulk and finds the minimal area surface anchored to that frame. Its area in Planck units equals the entanglement entropy of the region with its complement. Change the boundary state, change who's entangled with whom, and the soap film reshapes. The bulk geometry flexes because the correlation pattern changed. Spacetime isn't a canvas, it's a report. You can test the logic with toy models. Build a HOPPY code, an explicit holographic error-correcting network that tiles a hyperbolic disk. Bulk operators push to the boundary through isometries. Cut away a wedge of boundary legs and ask which bulk points remain reconstructible. The answer carves out an entanglement wedge whose boundary is the minimal surface. Move the cut around and the wedge slides through the interior, picking up and dropping bulk points. Locality inside is defined by which sets of boundary qubits co-reconstruct which logical operators. Here and there are statements about shared decoders. This flips a sacred intuition. We don't place particles into pre-existing rooms. The rooms materialize when the code supports local operators that commute like neighbors. If you dilute entanglement across a cut, less shared entropy, the minimal surface area shrinks or grows, distances change, and paths lengthen. In extreme cases, entanglement can be tuned to stitch separate bulks together into a wormhole-like bridge. The equals EPR slogan captures the vibe. Entanglement EPR can structure connectivity ER. Not sci-fi travel, but a statement that correlation makes corridors. Skeptics will say, that's de Sitter space and tidy disks. Our universe inflates and curves positive. True. Exact, provable dualities live in ADEST, but the recipe, relate geometry to entanglement, then track how surfaces extremize, has generalized. Quantum extremal surfaces and islands now compute entropy in more realistic setups, even explaining why Hawking radiation's entropy bends and drops after the page time. The soap films get quantum corrections, but the moral holds. Change correlations, change geometry. Here, where emergent gravity sneaks in again. If area tracks entropy and curvature responds to area variations, then Einstein's equations look like equations of state, constraints linking how entanglement changes to how geometry must bend. In Jacobson's thermodynamic derivation, Einstein's equations arise from assuming entanglement entropy is maximal in small regions, and responds to energy flux by an amount proportional to area change. Translated, if you keep local correlations at their preferred level and energy crosses a local Rindler horizon, curvature adjusts so the entropy balance stays optimal. Now bring it back to daily scale with a micro story. Two labs link quantum memories miles apart. They ramp up entanglement and suddenly teleport states with fewer errors. From their perspective, nothing moves faster than light. Protocols and classical signals still respect C, but from the code's perspective, those two memories just became closer in the metric that matters. They carved a shorter path through the network of correlations, so logical operations between them feel more local. Their bridge is math, not metal, but the effect is the same. Connectivity built from shared information. Once you see space as a function of entanglement, several puzzles settle. Why can't you just pick a point anywhere and act locally? Because local means supported by many overlapping boundary regions without disturbing others, and that support depends on the code. Why does cutting a system into parts create boundary terms? Because surfaces are where correlation breaks, and area counts that breakage. Why is energy tied to time translations while momentum ties to space translations? Because symmetries are constraints on how correlation patterns can shift without changing the ledger. And what about the big practical question? Can we measure this stitching? Indirectly, yes. Quantum simulators already realize tensor network ground states whose entanglement structure matches hyperbolic tilings. Teams probe how correlation lengths set emergent geometries in cold atoms and trapped ions. On the cosmology side, subtle imprints in the cosmic microwave background and large-scale structure encode early universe entanglement patterns. We aren't drawing soap films in a lab, but we are mapping the consequences of how they must have dipped. So you don't stand in space the way you stand in a room. You stand in a web of relations that decides, moment by moment, what counts as near or far, slow or fast, flat or curved, based on how information is shared. The walls are woven, not built. And every new correlation we write, every stitch we cut, helps the universe decide where here is. Constraints that look like engineered rules. By now the pattern is hard to ignore. The deepest laws read less like poetry about nature and more like specifications you'd find in a system design doc. Not because the universe is faking it, but because a world that must store, transmit, and recover finite information under strict causality ends up behaving as if someone engineered guardrails. Start with the speed limit. The speed of light isn't a suggestion. It's the maximum rate at which influence can propagate without breaking consistency. In a relational code, updates can only travel along allowed edges of the causal graph. Let influence outrun those edges and you create contradictions, effects without causes, records that can't be reconciled. So C isn't just how fast light moves. It's the bandwidth cap that keeps the ledger coherent across the code. Planck's constant does similar work at small scales. It sets the minimum action for an update, the base unit of change that makes quantum amplitudes interfere just so. Lower the quantum of action and you'd permit arbitrarily fine-grained writes, blowing up storage requirements. Raise it and you'd smear detail so coarsely that chemistry wouldn't stabilize. H looks like a tuning that balances expressiveness against cost, enough granularity for rich structure, not so much that the ledger overflows. Then there's the Bekenstein Bound, the boundary between fantasy and storage policy. It limits the number of bits in any region by its surface area. Try to exceed it and gravity forms a horizon, forcing a safe to surface. That's exactly what an engineered system would do when a buffer threatens to overflow, spill to a more reliable medium and throttle the right. The universe makes black holes. The Margolis-Levitin bound adds another rule: how fast a system of given energy can perform orthogonal operations. It's a clock speed tied to power budget. Together with C and the Bekenstein bound, it sets a triangle of constraints: how much you can store, how fast you can update, and how far those updates can reach. They don't feel personal, they feel architectural. Look at conservation laws through the same lens. Noether's theorem says symmetries imply conserved quantities. Translation symmetry gives momentum conservation. Time translation symmetry gives energy conservation. In code terms, invariances are assertions that certain transformations don't change the compressed description. If you shift a pattern and the complexity stays the same, the summary fields, the headers of the state, must remain constant. That stability is what lets you build hierarchies of description without contradictions. It's also what keeps prediction possible. Even renormalization, the dreaded technical machinery of quantum field theory, looks like an engineering protocol. You coarse-grain, absorb divergences into redefined parameters, and insist the long-distance behavior stays finite and predictive. In networks, the analog is multi-scale compression that preserves relevant information while discarding noise. The parameters flow because you're changing resolution, not because the universe wobbles. That flow stabilizes near fixed points, where the code becomes scale invariant and universality emerges. Different microscopics, same macroscopics, many encodings, one effective behavior. Error correction tightens the impression. Holographic codes don't just happen to be redundant. They must be, or the bulk would be illegible. Logical operators spread across many boundary qubits so that local faults don't corrupt meaning. You can flip a few bits and the decoder still retrieves the interior. That's exactly how robust storage systems are built. Distribute, replicate, reconcile, all to deliver a stable view to higher layers. The bulk is a high-level API that doesn't crash when a disk blips. Thermodynamics rounds out the rule set. Landor costs make information processing pay with heat. The second law guides the typical direction of computation towards states that are easier to encode because they have more micro descriptions for the same macro constraints. Ergodicity assumptions become scheduling policies. Over long runs, the system explores enough of its state space to justify statistical descriptions. It's not destiny. It's what tends to happen when finite energy chases finite memory under noise. Skeptics push here. Constraints don't imply design. True. Evolution gives you the same vibe. Selection pressure sculpts what works. The point is that a programmer tuned constants on a bench. It's that a universe obligated to obey unitarity, causality, and finite capacity will settle on rules that look suspiciously like sensible engineering, because those are the only rules that keep contradictions at bay. The design is logic plus survival. Unstable rules don't support long histories with reliable records. Stable rules do. This turns fine-tuning on its head. We notice precarious balances, cosmological constants small, couplings just right, and debate intent. An information-first view asks a different question. Which ranges of parameters permit scalable, error-correctable computation that yields rich, decodable structure before horizons, noise, or freeze-out choke the process? The observed window might be where the code runs longest and recovers best, not a cosmic coincidence so much as a viability zone for extended histories. Microstory, an aerospace team builds a flight control system. They cap data rates, quantize sensor inputs, enforce checksums and separate concerns across layers. They didn't copy the universe. They converged on the same solutions because the same problems, finite bandwidth, noise, latency, force the same strategies. Now scale up. The constants and laws we measure are like those strategies. They are those strategies expressed in the algebra of fields and geometry. So no, nothing here proves intention. But it does reveal why physics feels engineered. The world behaves as if optimized for consistency, compression, and recoverability, because that's what it takes for reality to persist as an ongoing, legible record. In that light, the elegance we celebrate isn't decoration. It's the signature of constraints doing their quiet, relentless work, so the universe can keep telling its story without losing the plot. Origin, from simple rules to rich worlds. If the universe behaves like code, then the next question isn't mystical, it's practical. What's the minimal instruction set that can unfold into everything we see? Not a library of laws, just a recipe simple enough to run anywhere and still bloom into chemistry, stars, life, and minds. We've seen a hint before. Conway's game of life runs on rules a child can memorize. Cells live or die based on their neighbors. That's it. Yet gliders cross the grid, oscillators tick forever, and tiny programs compute within the chaos. The lesson isn't that we live on a checkerboard. It's that simplicity can beget unbounded complexity when local rules feed back on themselves. Digital physics chases that lesson at cosmic scale. Replace cells with events. Replace neighbors with causal adjacency. In causal set approaches, you add elements and specify who can influence whom, never breaking the order that keeps causes cleanly ahead of effects. No lattice spacing, no global clock, just relations. From that, continuum spacetimes can re-emerge statistically, like how temperature emerges from molecules you never individually track. In Wolfram's hypergraph program, you start with a graph and a rewrite rule. When this pattern appears, replace it with that pattern. Apply everywhere you can, again and again. The space is the graph itself. Its degree of connection defines locality. The time is the sequence of rewrites, though many orders can lead to the same causal structure. From this, Lorentz-like symmetries may appear as features of the rewrite graph's causal network, not assumptions glued on top. Sabine-Hassenfelder's warning about naive discretization still stands, and that's the point. These frameworks dodge rigid grids by elevating relations, aiming to let symmetry show up as a property of the build, not a nail you hammer later. But rules alone don't give you planets. You need pathways from small to large. That's where renormalization, tensor networks, and emergent effective theories do the heavy lifting. Start with bits and relations. Coarse-grain them without losing what matters. The low-energy fields, the quasi-particles, the equations we teach in freshman classes, those are compressed summaries of deeper, busier layers that hide their microscopic specifics behind universality. Different micro-rules, same macro laws, the way many different circuits can implement the same logic gate. Holography sharpens this path. Begin with a boundary quantum system that satisfies unitarity, a finite capacity constraint, and robust entanglement structure. Feed it a simple Hamiltonian, local interactions on a lattice, or a conformal field theory with well-behaved operator growth. Let it run. Entanglement spreads like dye in water. Minimal surfaces in the dual bulk expand and warp. Geometry inflates from correlations, then ripples with the energy momentum flow. What looks like a gravitational wave in the interior is, at the edge, a wave of changing entanglement across degrees of freedom. What looks like a particle is an interior operator supported redundantly on boundary regions. You didn't build planets by hand. You let the code's policies, compression, recoverability, causality, decide what counts as a stable excitation, then watch those excitations assemble into structures that endure. Gravity looks inevitable in that process. If the code prefers encodings that minimize area for a given entanglement, then patterns of energy that change correlation distributions will demand curvature as bookkeeping. That curvature, at large scales, enforces trajectories that conserve the right summarizes, energy momentum, while keeping decodability within budget. Einstein's equations read as the equilibrium condition of an informational fluid. Change the local entanglement by feeding energy through a light sheet, and the area must adjust in proportion, or your code would lose track of who is with whom. Life fits too, without romance. Chemistry is the playground of effective rules that stabilize complex, metastable arrangements under noise and heat, proteins folding into energy basins, reaction networks that self-maintain, replicators that exploit redundancy to survive errors. Computation blooms wherever there's free energy, and a medium that supports symbolic dynamics robust to perturbation. DNA is a molecular code with error correction. Neural tissue is a predictive machine that compresses streams of sensory data. None of this violates physics. It's physics leaning into its own constraints, birthing subroutines that learn to spend energy to reduce uncertainty. There's a micro-story buried here. A student writes a few lines of code to simulate a rule on a graph. Night after night, she tweaks the update, one more constraint, a different priority for pattern matching, and watches emergent traffic stabilize, then jam, then self-organize into lanes. She hasn't programmed cars. She's programmed rules that make car-like flows the cheapest stable outcome. That's a sketch of cosmic history. Not cars, fields, atoms, stars, but the same trick. Find the low-cost, high-redundancy patterns that the code can represent and protect with minimal overhead. Those are the things that feel real to creatures like us. Could different simple rules yield other universes? Quite possibly. Some would freeze, unable to compute rich structure. Others would boil, noise overrunning any hope of legible records. The sweet spot is narrow. Rules that allow growth of entanglement without immediate saturation, causal propagation without contradictions, redundancy without paralysis. We exist because our rule set sits in that viability zone where long histories can accumulate without the ledger failing. None of this proves intent. It demonstrates sufficiency. From minimal, relational rules and hard constraints, unitarity, causality, finite capacity, you can grow worlds that look like ours. Continuous at scale, quantum underneath, curved where energy weaves space tighter, classical where error correction makes records stick. The wonder isn't that the code runs. It's that the same policies that keep it consistent also make room for us to arise inside it, ask questions, and trace the rules back to their simple beginnings. Are we simulated? Tests, clues, and dead ends. Here's the uncomfortable question that keeps sneaking back in. If reality looks like computation, are we inside someone else's program? It's tempting to leap from the universe computes to the universe is a simulation. Tempting and sloppy. Still, there are tests people have chased, clues they've hunted, and dead ends that taught us what's actually measurable. Start with the cleanest idea. Look for the grid. If space were literally pixelated on a fixed lattice, ultra-precise experiments should catch tiny violations of Lorentz symmetry, preferred directions, energy-dependent speed-of-light shifts, anomalies in high-energy cosmic rays. Physicists have looked. Observatories, colliders, and tabletop setups have pushed those bounds mercilessly. The signature jaggedness never showed. As Sabine Hassenfelder argued, any rigid discretization clashes with relativity because a lattice that's fine for you looks coarser for a boosted observer. If you can see the pixels in one frame, some other frame sees contradictions. That root likely closes unless the substrate is relational, not a ruler, but a web of causal links that let symmetry emerge. What about cosmic grain in spacetime itself? Experiments like GEO 600 and LIGO have been tuned to search for holographic noise, subtle jitter consistent with finite information at Planck scales. So far, the data behave. If there's holographic fuzz, it's quieter than current sensitivity. That doesn't falsify holography. It just means the universe, if pixelated, hides its pixels in correlations, not in easy-to-spot static. Then there's the black hole angle. If we're in a simulation, maybe fine-tuners left fingerprints in the way black holes handle information. Odd kinks in Hawking radiation's entropy curve, imprints that shouldn't be there. But the opposite happened, theory sharpened. Quantum extremal surfaces and islands reproduce the page curve in solvable models, precisely the way a unitary, error-correcting code would demand. The more we learn, the less room there is for sloppy bookkeeping. Whatever our world is, it keeps its ledgers straight. What about cosmic rays? Some propose that an underlying lattice would cap particle energies or create direction-dependent anomalies in the highest energy events hitting Earth. Detectors like the Pier Auger Observatory set hard limits on such effects. Again, nothing. Either there's no simple lattice, or the encoding is too subtle to betray itself that way. Nick Bostrom reframed the question with statistics instead of microscopes. If future civilizations can run vast numbers of ancestor simulations, And if simulated minds are subjectively indistinguishable from base-level minds, then most minds would be simulated. Therefore, odds say we're simulated, unless advanced civilizations don't survive or don't run such simulations. That's a clean argument. It's also one you can't test from inside. You can debate the premises, survival, ethics, resource limits, but no experiment distinguishes base from sim. If a perfect simulation updates every memory, record, and law consistently, any change would rewrite the evidence too. Computerphile's take was more grounded. Try to catch quantization in the wild. If space and time are discretized, maybe we'd see aliasing artifacts, spectral lines slightly shifted, interference fringes subtly clipped, propagation limits in particle behavior. But that slides back into the Lorentz trap. A relational substrate avoids those telltales by never picking a universal frame. The test becomes, can you spot relational inconsistencies? Our best checks, Bell tests, Lorentz invariance, CPT symmetry say no. The rules are tight. Another gambit, find the bug. If we're in a program, perhaps there are edge cases, cosmic coincidences that look like hacks, arbitrary constants patched mid-run, sudden rule changes, retroactive edits. The problem is obvious. Any edit that preserves consistency will also update your memories, instruments, and records. You can't catch the switch if the switch rewrites the catcher. We're back to untestable whispers. So what's left to measure? Holographic structure offers indirect probes that don't assume an external simulator. If area really tracks entropy, there should be consistent relations between entanglement patterns and geometry. That's where real progress is. The page curve in solvable models bends as unitary evolution demands. Entanglement wedges reconstruct interior operators redundantly, exactly what error-correcting codes predict. In labs, quantum simulators mimic these mappings. Tensor network ground states display geometric features tied to correlation. None of this says simulation. It says computation is how the universe behaves. Seth Lloyd's estimate that the universe has performed roughly 10^120 operations on about 1090 bits sometimes gets twisted into, we're running on a computer. He meant something narrower. Physical law lets you count operations and memory as if the universe were computing. That's not metaphor, it's a framework. But it doesn't imply an external server farm any more than thermodynamics implies a celestial boiler. Here's a sharper distinction. Simulation is an externalization claim. There exists a separate substrate running this world. Digital physics and holography are internalization claims. Information processing is what this world is. One invites theological arguments about programmers. The other invites experiments about entanglement entropy, error correction, and emergent geometry. Only one pays off in labs. Still, the itch remains. Could we ever know? If the simulator wanted to be known, they could break consistency, leave a signature that violates quantum mechanics or relativity in a way we can all agree isn't a fluke. If they don't, every test collapses into the same conclusion. Reality behaves like a self-contained information processor that guards its constraints fiercely. That's what our measurements show. So we keep our curiosity disciplined. We look where physics pays rent. In the way black holes return information, in the geometry entanglement ledger, in the limits that look like engineered rules because they're the only stable ones. The simulation door stays philosophically ajar. The empirical hallway we can actually walk is narrower and far more interesting. Life, mind, and the compression game. If the universe favors encodings that are consistent, compressed, and recoverable, then life looks less like an exception and more like a signature feature. It's what happens when matter learns to compress experience fast enough to keep pace with noise. Cells, nervous systems, and cultures aren't escaping physics. They're surfing it, turning scarce energy into reliable bits that help predict the next input before it lands. Start small. A bacterium swims up a sugar gradient. It doesn't solve calculus. It compresses a history of receptor hits into a simple bias. More hits, keep going, fewer hits, turn. That compression is lossy on purpose. It throws away detail that doesn't change the decision. Every microbe is an information engine, burning chemical-free energy to reduce uncertainty about what action will keep it alive for one more minute. Landor would nod. Those overwritten bits have a heat trail. Scale to brains. Neurons fire to minimize prediction error. They build generative models that compress the world's regularities into internal codes that can be updated quickly when surprises arrive. Memory isn't a shelf of perfect files. It's a reconstruction machine that reuses patterns to rebuild an adequate past on demand. Redundancy makes recall possible. Forgetting is a feature, not a bug. It frees capacity for patterns that pay in future survival. Consciousness enters as the felt side of this compression game. You don't perceive raw data. You perceive an interpretation your brain finds most efficient for action. Colors, edges, objects, those are interface icons built from predictive codes. The self that narrates your life is a high-level summary variable that stabilizes control under noise. You're experiencing the output of a model that keeps updating to keep loss low. The costs never vanish. Attention is a budget. Sleep is maintenance where synapses downscale, pruning redundancy that stopped paying. Learning is gradient descent through hypothesis space, paid for in ATP and time. Emotions are priority flags that bias updates. Fear speeds encoding of threat patterns. Joy widens the search over possibilities. These aren't metaphors. They're the biology of an information processor allocating scarce compute. This dovetails with the holographic architecture beneath. Perception stitches local geometry from correlated signals. It's a personal entanglement map built from light, sound, and touch. When many minds synchronize, language, music, ritual, they braid their internal codes, increasing redundancy across individuals so ideas can survive beyond any single brain. Culture is error correction at species scale. Overlapping encodings of stories, tools, and norms that keep meaning alive across noisy generations. Technology amplifies this strategy. Writing externalizes memory to surfaces, stone, paper, silicon, freeing neural capacity for higher-level compression. Scientific models are boundary codes that let us reconstruct interior truths from partial data. Quantum error correction moves from metaphor to hardware as we fight decoherence with redundancy and clever decoding. Every library, lab, and server farm is a heat-emitting monument to our species-wide attempt to keep and compute useful patterns under the same constraints that bend spacetime. The dark side is predictable. Mesencodings propagate when they exploit bias and bandwidth, rumors that compress too well, incentives that reward short-term loss of nuance. Information pathogens spread because they fit the channel. The antidote isn't outrage, it's better codes, institutions that raise redundancy, improve verification, and penalize easy compression that destroys truth. Ethics in this frame is about protecting decodability, choices that preserve the capacity of others to reconstruct accurate models of their world without paying impossible costs. Free will becomes less binary. You aren't outside the code, you are part of it. Agency is the way a predictive model can alter its own priors under new evidence, subject to constraints. Within your bandwidth and energy budget, you can choose updates that change how you compress experience tomorrow. That choice registers physically. Synapses reweight, habits shift, trajectories diverge. It's not metaphysical freedom. It's computational autonomy within the policy space allowed by the rules. Meaning fits too. In a universe where most states are noise, meaning is a rare pocket where compression rates spike, structure recurs, predictions land, and records endure. Love, craft, discovery. Each is a long correlation thread woven through time, robust to loss because it's redundantly encoded across actions, memories, and communities. That's why meaning feels solid. It survives errors. And mortality. If the boundary keeps the ledger, no individual code runs forever. Heat death is the far horizon where gradients fade and the cost to compute any new structure exceeds the budget. But that's not our era. We live in a window where gradients abound and redundancy scales. Our task isn't to beat the rules. It's to use them, to build systems that waste less heat on noise and spend more on patterns worth keeping. So the mind isn't a ghost in the machine. It's the machine's most efficient trick, a living compressor that turns chaos into models that stay just ahead of what comes next. Life is the part of the hologram that learned to write back to the boundary, carefully, redundantly, so the story can go on. Ethics, purpose, and behavior in a data reality. If reality is information, ethics becomes about preserving decodability. The good choice is the one that keeps truth retrievable at bearable cost. The bad choice corrupts records, overloads channels, or burns energy to amplify noise. That sounds abstract until you map it onto daily life. Lying spreads patterns that require more energy to reconcile later. Exploiting attention hijacks bandwidth that communities need to correct errors. Pollution isn't only carbon, it's informational. Manipulative narratives, opaque systems, brittle incentives. In an information-first world, responsibility starts with protecting the conditions that let minds form accurate models without paying impossible thermodynamic bills. This reframes freedom. You still have agency, but it's not licensed to write any string. It's stewardship over your local write permissions in a shared code base. Your choices propagate, they entangle with others' records. So ask, does this update increase redundancy for critical truths, or does it reduce them? Does it compress complexity without erasing nuance? Does it make recovery easier after shocks? That's an ethic of resilience. Prefer actions that raise the probability that meaning survives when channels fail. Purpose shifts with it. If most states are noise, then meaning is rare order. Purpose is the practice of sustaining those pockets, not by freezing them, but by building codes that flex without breaking. Families, labs, cities, each is an error-correcting network. They thrive when participants spend energy on verification, transparent feedback, and graceful rollback. They fail when shortcuts reward compression that destroys signal, outrage loops, clickbait, winner-take-all optimizations that flatten diversity into viral sameness. The ethic is simple and hard. Build structures that keep many perspectives decodable within the same ledger. Justice becomes more than punishment, it's system repair. Harm isn't only pain, it's distortion, lost data, broken channels, coerced updates. Repair means restoring bandwidth to those cut off, rebalancing redundancy where it was stripped, and ensuring future rights aren't silently overwritten. That's why due process matters. It's slow on purpose, trading throughput for reliability. And why transparency matters. Hidden states force observers to guess, burning energy and trust. Truth grows teeth in this frame. It isn't an abstraction floating above the world. It's a set of encodings that let different minds reconstruct the same event within error bars. Institutions that protect truth do so by raising the cost of corruption and lowering the cost of correction. Open data, reproducible methods, adversarial review. When those norms erode, society spends more heat reconciling contradictions, leaving less for building new structure. Cynicism is not skepticism. It's surrender to cheap compression. Technology is force multiplier and risk. Quantum computers, large models, ubiquitous sensors, they widen our write capabilities. The ethic isn't reflexive fear or blind acceleration. It's interface designed for decodability. Bias audits, provenance tags, rate limits, incentives aligned with long-term redundancy. That means saying no to architectures that privatize signal and socialize noise, and yes to ones that price externalities at the point of write. In energy grids, that's carbon accounting. In information grids, that's friction for virality without verification. Privacy doesn't vanish, it gets clarified. In a holographic reality, everything is entangled, but decodability is domain-specific. Ethical privacy is about limiting who can reconstruct which logical operators, who can decode which aspects of you. The wrong is not correlation, it's extraction without consent, reconstruction that strips agency. Good governance sets entanglement wedges with care. Enough overlap for safety and service, not so much that individuals lose the capacity to manage their own updates. Education becomes rehearsal for ethical rights. Teach compression that preserves meaning, statistical literacy, model uncertainty, cognitive biases. Teach error correction, how to disagree cleanly, how to retract, how to version ideas. Teach thermodynamics of knowing, attention budgets, sleep limits. Teach how to build redundancy without echo chambers, diverse networks, slow deliberation, fast alerts with sober follow-up. Spiritual questions don't evaporate, they translate. If consciousness is a process of modeling under constraint, reverence can be the felt recognition that other beings are running precious, costly encodings too. Compassion is costly on purpose. You spend energy to keep someone else's decoder from failing. All becomes gratitude for a cosmos whose constraints allow beauty to stabilize long enough for anyone to see it. Humility acknowledges undecidables, the questions no system inside the system can resolve, and keeps dogma from hard-coding over live code. You can test this ethic with small acts. Before you share, ask whether you've raised or lowered the energy future others must spend to reconcile the post with reality. Before you optimize, ask whether the gain will brittle the system, remove slack, cut checks, collapse diversity. Before you design, ask where your users' right permissions might be exploited and how you'll make rollback possible. These aren't platitudes, they're policies that reduce catastrophic cascades. And when systems fail, and they will, remember the code's preference: graceful degradation. Build fail-safes that preserve the most crucial encodings under stress: clean water, truthful communication, care for the vulnerable. In black hole language, protect the horizon ledger. In civic language, protect rights that maintain decodability. Free speech with accountability, due process. A press that can correct itself, science that can admit error. Meaning doesn't arrive from outside. It emerges when many agents choose updates that keep shared structure recoverable. That's an ethic you can live today. Reduce noise, amplify verified signal, design for redundancy, spend energy where it preserves the capacity of others to know and choose. In a universe that runs on information, purpose is simple to say and endless to practice. Help the story stay legible. Return to the screen, what the silence meant. Go back to the quiet moment we skipped past, the pause after the question that started all of this. Not the question about simulators or programmers. The smaller, sharper one. If everything is information, why does the world feel so solid, and why does it keep going when you're not looking? The silence wasn't empty. It had a cost. Remember Landor, every reliable bit takes energy to write. That quiet room with the sleeping laptop, the dark phone, the still air, it was humming with stored decisions. The wall paint reflected the same spectrum it did yesterday because molecules settled into a configuration the code finds cheap to keep. The chair held you because its bonds are stable summaries enforced by quantum rules that punish deviation. Nothing waited for you. It persisted because redundancy made your absence irrelevant. Silence meant the code didn't need your attention to balance its books. Gravity didn't pause. Entanglement didn't slacken. The boundary kept writing, whether anyone admired the handwriting or not. That's uncomfortable if you've grown used to a universe that stars you. But it's freeing too. You aren't responsible for keeping the lights on. You are responsible for how you spend the narrow beam of attention you get. Think about the night sky as a ledger you can read but not edit. Those galaxies aren't images on a dome. They're threads in a computation that began long before language, still paying its energy bills one photon at a time. The silence between stars isn't empty. It's bandwidth no one's using right now. If you had instruments sensitive enough, you'd hear the hiss of microwaves from the first light that could travel, the whisper of gravitational waves from black holes blending, the crackle of cosmic rays. The quiet is simply what it sounds like when a ledger is mostly balanced. We learned the rules inside that silence. Black holes don't crash the program, they enforce it. Add SCFT didn't flatten wonder. It deepened it, showing that geometry is a living index of entanglement that keeps meaning recoverable. Error correction wasn't a metaphor. It was the reason you could trust tomorrow to resemble today after you slept. Every law we traced, C, H, area bounds, read like constraints the world had to respect to keep being a world and not a smear of contradictions. What does that ask of you? Not to decode every layer, not to pretend there's a backstage. It asks for care with rights. The words you choose sit on surfaces, screens, ears, eyes, and they either raise or lower the cost someone else must pay to get back to truth. The designs you ship either keep systems graceful under strain or make them brittle. The habits you cultivate either build redundancy into your life, friends who can reconstruct you when you falter, or isolate you behind a fragile encoding. The silence also meant there are questions you won't answer from inside. That's not a failure, it's a fact about finite systems. Some puzzles, why these constants here, why this boot sequence, will stay undecidable at our layer. You can waste heat arguing, hard-code your ignorance into dogma, or use the saved energy to refine the models that do pay rent. Better reconstructions, safer codes, kinder defaults. There's a micro scene that keeps returning. A kid walks home at dusk, phone dead, stars barely visible through city glow. No music, no notifications. Just footsteps, breath, and the subtle change in air when a street opens to a park. If you could translate that moment into physics, you'd see entanglement maps updating with each step, tiny gravitational gradients nudging trajectories, neurons burning ATP to compress sounds into a model that says safe. The child doesn't need to know any of it. The quiet is full enough. Maybe that's the real point. Calling the universe just data undersells it. Information isn't a spreadsheet. It's the difference that makes a future possible. The world feels solid because the code spends what it must to keep structure intact. The world feels beautiful because those structures, under tight constraints, discover symmetries that make compression look like grace. So we return to the screen with a different posture. Not as debunkers, not as worshippers, but as collaborators in a system that runs fine without us, and runs better when we write carefully. We don't need to break the hologram to be honest about it. We can love the projection while learning the policy that keeps it stable. We can accept that the silence means the story doesn't revolve around us, and still decide to make our sentences worth the heat. Meta-render, the observer as model maker. We've been talking about codes and constraints as if they sit out there, but the story isn't complete until we turn the lens around. You're not a passive pixel in a grand render. You're a meta-render, a system that builds a world model on the fly, compares prediction to sensation, and updates under cost. The observer isn't just watching the computation. The observer is a computation that makes the watching possible. Start with a simple loop. Sensory streams hit your receptors, photons, pressure, chemicals. Your brain pushes a guess downward through its hierarchy. This edge is a cup. This tone is a friend's voice. This movement means step left. The incoming data is compared with the guess. Mismatches generate error signals. Then you update the model or the action plan. That's predictive coding in plain clothes, a compress, predict, correct cycle that minimizes error under an energy budget. It's the same logic that makes the universe favor recoverable stories, now running at mammalian speed behind your eyes. You can feel this loop when it fails. Walk into a dark room and misread a coat as a person. Your model overshoots, error spikes, your stomach drops, you update. Listen to a sentence in a loud bar. Your brain fills the gaps with context, then revises when a word snaps into focus. The aha is the cost you paid to settle on a better compression. It's not mystical. It's your model locking onto a less expensive code for the same signal. Now layer in agency. You don't just passively accept flows. You act to make prediction easier. You move closer, slow down, squint, ask a question. Action is information gathering under constraints. You steer your sensors into regimes where the model's uncertainty drops for the least metabolic spend. Babies do it with faces. Scientists do it with telescopes. The meta-render chooses the next measurement to reduce error where it matters. This is where perspective enters the physics honestly. We asked earlier, whose steps? Whose time? The answer wasn't a cosmic clock, it was causal order plus local records. Observers like you are record makers with priors. Your world model carves a now through the ledger that serves your actions best. That doesn't change the ledger, it changes how you query it. Two observers moving differently slice different nows and still agree when they meet, because the underlying code guards consistency. Your role is to pick a slice that keeps your predictions useful. The holographic story fits cleanly here. Your perceptions are boundary reads that reconstruct an interior scene. You never see all the qubits. You sample edges, photons from a surface, echoes from a wall, and your cortex runs a decoder trained by a lifetime of correlations. That's why illusions work. They feed your boundary with patterns that usually decode to a certain bulk, and you accept the reconstruction until error forces a rewrite. The art of perception is choosing which entanglement wedge to trust for which task. Memory closes the loop. You don't store high-definition tapes, you store parameters of models, weights on edges, prototypes for categories, scripts for common events. Recollection is reconstruction. When a smell cues a childhood kitchen, your brain pulls a plausible bulk from sparse boundary hints. Sometimes it's wrong, sometimes it's eerily precise. Redundancy helps. The more overlapping encodings you lay down, photos, conversations, muscle memory, the more robust the recovery. Forgetting is pruning encodings that stop paying. It hurts because it frees room for accuracy next time. You've noticed how attention feels scarce. That's not an illusion. It's the real cost of running this predictive machine. Each focus narrows the bandwidth you can spend elsewhere. Each task switches contexts, paying an overhead to rehydrate a different model. Multitasking isn't heroic. It's lossy interleaving that leaves more error on the table. The physics of knowing shows up in your day as fatigue after too many writes and reads. Now zoom out. Groups are model makers too. A lab, a newsroom, a rescue team, they each operate as a higher-level observer that seeks signal, compresses it, publishes a story, and updates under feedback. Their ethics are the same as yours. Prefer decodings that preserve decodability. Don't collapse nuance into virality if it breaks future recovery. Don't hide priors. Don't overfit to noise. When they fail, you see it as scandal or confusion. When they work, you barely notice because your error dropped and you moved on. This is the meta-render's humility. You are always inside your own model, never outside the computation. You can improve your priors, education, exposure, practice, but you will never see the code directly. That's okay. Physics doesn't require that you step outside. It invites you to build better decoders, test them against the ledger, and accept the limits with grace. It also grants a kind of mercy. If your experience is a controlled hallucination kept honest by sensation, then compassion for other observers is built in. Their models are tuned by different priors, different costs, different noise. You can demand accountability for harmful writes while still recognizing that correction always has a price. Good discourse lowers that price. Slower pace, clear evidence, shared frames, so more minds can converge without burning out. Finally, the meta-render can aim itself. You can choose what to model deeply, craft, friendship, a field of study, and what to leave coarse. You can surround yourself with redundant encodings that restore you when you wobble. You can design your interfaces, news, work, tools, so they don't hijack your error signals for profit. You can build habits that keep your decoder honest. Sleep, walks, time with no rights, time with deliberate rights. You're not watching a movie the universe made. You're co-authoring your scene, line by line, under the same constraints that hold galaxies together. That's not less real. It's more intimate. The observer as model maker isn't a demotion of truth. It's an instruction for how to find more of it with the energy and bandwidth you actually have. Meaning in a computed cosmos. If reality is information, solidity is what redundancy feels like, and beauty is compression doing its quiet work. You don't need a master clock or a hidden programmer to matter. You have right permissions. If you want more stories like this, evidence-rooted, human-centered, subscribe now. And watch the next episode, where we follow one black hole's ledger from collapse to page time to evaporation, and ask what returning information really means.